Okay, welcome back, everybody. At the end of yesterday's lecture, we were seeking what we called these fundamental solutions to Laplace's equation. And the kind of path to this was I noted that, oh, well, this operator, the Laplacian, in Laplace's equation, this expression here is rotationally invariant, meaning that if I change variables from like normal triple in space to some rotated triple. So I take my normal coordinates in space and I apply a rotation to it, right, and get new coordinates, x1 prime, x2 prime, x3 prime. Then I can, if I compute the Laplacian with respect to these new coordinates, it's actually exactly the same as the old Laplacian, right? The only thing that's changed here are the actual coordinates. So this Laplacian of U is rotationally invariant in this sense with respect to those spatial variables. And so it makes sense to seek solutions to Laplace's equation that only depend on that radius, right, on that distance to the origin. So here's, of course, what our distance to the origin looks like. So then we are seeking functions, even though it's also a function of x, really it only depends on the length of the vector x, right? So if x is some point in space, actually what matters is its distance to the origin, is what we're seeking. And so we're actually seeking a function of this variable r, where r is our distance to the origin. Okay, so how does that help me? So first of all, let's go ahead and suppose, again, I said this is really only interesting if the dimension is at least 2. Right, so for dimension 2 and greater, the question is uh, what this does for me. So first of all, let's quickly compute the partial of this new expression r with respect to each of the variables, x sub I here. So what is like the partial? Let me give myself more room here. So what is the partial of r with respect to, say, an individual x sub I? Well, so let's see. So this is that sum from x1 squared to x of n squared. Um, and I'm taking the square root of that. So that taking the derivative of this with respect to an individual x sub I is going to be 1/2 times this same expression raised to the minus 1/2, right? So this is going to be x1 squared plus dot 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 x sub n squared raised to the minus 1/2 times 2 x sub I, right? The derivative or the partial derivative of what's inside with respect to the x sub I. So this is 2x sub I. And so the 1/2 and the 2 cancel, and what I'm left with is x sub I over this sum. So this is x1 squared plus dot 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 x of n squared to the 1/2. Oh, but wait, like that sum is exactly r, so really this is just x sub I over r, right? So this altered expression here is this is not so bad, right? So the partial derivative of this expression for r with respect to an individual x sub I is just x sub I over r. All right. So then, using the chain rule here, this partial of u with respect to x sub I is what this is. Since u of x sub, so u is defined to be this v of r here. So I'm taking this x sub I partial. This is v prime of r times the partial derivative of r with respect to x sub I, which is x sub I over r, right? Okay, so I can compute that partial. And of course, now I can take the partial of this with respect to x sub I again. So u sub x sub I, right, is now again applying all my derivative rules, right? Product rule and chain rule here. What do I get? This is v double prime of r times x sub I over r times x sub I over r, right? That I get from differentiating this again. Okay, plus v prime of r times the partial derivative of this thing with respect to x sub I, which is, so here I have to be careful. So I'm differentiating this thing with respect to x sub I here, but of course r depends on x sub I as well. So being careful with how I compute this derivative and its algebra, I would get 1 over r, right, minus, computing now the derivative of the denominator, this would be x sub I squared over r cubed after all of the algebra is done here. Okay. Rewriting this real quick, this is like v double prime of r is x sub I squared over r squared, and plus v prime of r times 1 over r minus x sub I squared over r cubed. Yeah. Okay. Okay. So if this is what u sub xi is, then, sorry, and this is what u sub xi is, then Laplacian of u, of course, is the sum of each of these things, right? All the way to n. So I want to sum this expression from I equals 1 to n. What do I get if I do that? So I'm going to get, so this v double prime of r doesn't depend on I, right? So it doesn't care. This isn't indexed. So in my sum, I can pull that out of the sum. So this would be v double prime of r times the sum now from I equals 1 to big N of x sub I squared over r squared. Right, again, r doesn't depend on I here, so I can pull it out of the sum. Okay, plus v prime of r times summing 1 over r from 1 to n is there, so there's n copies of this, so this would be n over r. Right, minus the sum from I equals 1 to n of x sub I squared over r cubed. But of course, the sum from I equals 1 to n of x sub I squared, that's just r squared. This is r squared, right? So rewriting this, this is v double prime of r times r squared over r squared plus v prime of r. My v's and r's are looking really similar here. Times n over r minus r squared over r cubed. So this is v double prime of r plus v prime of r times n minus 1 over r. Okay, so the Laplacian of u turns into this ODE with respect to the variable r for my radial function v. Remember, v is u. It's just u considered as depending on the distance, right, of x from the origin. Okay. And so what have we shown here? We have shown that the Laplacian view is equal to 0 if and only if this ODE is satisfied, v double prime plus n minus 1 over r times v prime is equal to 0. That is what we've shown. Right. Again, my r's and v's looking too similar here. There we go. Okay. All right. So here's the ODE now that I want to solve. So let me rewrite this. So we have an ODE to solve v double prime plus n minus 1 over r v prime is equal to 0. To get rid of the trivial constant solutions to this, but look, each term involves a derivative, so of course constant solutions are going to satisfy this. So let's get rid of those. So let's assume that v double prime is not equal to 0. All right, because we're less interested in the constant solutions. Then, if v prime is not 0, I can rewrite this ODE. I can rewrite this ODE in the following way, right? So this is like, I can write this as the derivative of log of the derivative of v. Right, so what is this? This expression is v double prime over v prime. But if I can divide by v prime because it's non-zero here, that has to be, by this equation, that has to be minus n minus 1 over r, which is 1 minus n over r. So why would I want to rewrite it like this, where I'm taking a derivative on the left-hand side? Well, now I can integrate both sides, right? So integrating both sides, this is with respect to r. So this is log of absolute value of v prime is what is, how do I rewrite this? So this is, now I'm integrating this thing with respect to r, so this is going to be log of r. Well, it's going to be 1 minus n times log r, but I can rewrite that as log r to the 1 minus n using log rules. Okay, plus some constant, I'll call it c. All right. Of course, another way of writing this, and I'm not saying that this is the same c, I'm absorbing this constant. Another way of writing this is to just say that the absolute value of v prime is, say, c over r to the n minus 1. Okay, both of these are equivalent. Again, this is not necessarily the same c here. I'll write it as c naught if you really want to. Okay. So, now integrate again. What do I get from here? I get the following. So, this, when I integrate this quantity, this denominator here, it matters what n is, right? If n is equal to 2, I get a log, because now my denominator is just r. So integrating with respect to r, I'm going to get a log. If n is bigger than 2, I'm just going to get, some r in the denominator here, right? So what do I get? It depends on the dimension, but there are two options. So this is some c1 log r, right, plus some c2 if our dimension is 2. And if our dimension is 3 or bigger, I get C1 over R to the big N minus 2 plus C2 if N is 3 or bigger. All right, that's my solution to this. Okay. Now, you can just check that if actually this had occurred at any single point, then that would have led to a constant solution. And so this assumption that v prime is not 0 anywhere in this expression is fine. So we have found all of the possible radial solutions. Okay, and so apart from those constant solutions that we didn't include, notice that each of these blows up at r equals 0. Well, at r equals 0, that's distance 0 from the origin, i.e. that's the origin. Right? Okay. All right. So, what does all of this mean, right? It means that if we're building our fundamental solution out of this, then these fundamental solutions are also going to blow up at the origin. Okay, and it turns out that's exactly what happens. So how can we use this to define the fundamental solutions? So the idea, we choose particular values of C1 and C2 to write our fundamental solutions to Laplace's equation. Okay. You'll see what is informing our choice of these constants in a second. All right, but for now we're picking particular constants here to do this. Okay. So the fundamental solution for the Laplacian in dimension n, which is bigger than or equal to 2 here. Nope, I'm off screen. Is defined to be v of x, which is in the dimension 2 case 1 over 2 pi times log of the length of x. This is in dimension n equals 2. So that's our choice of that constant in dimension n equals 2. In dimension n equals 3, this is minus 1 over 4 pi times length of x. Notice the relationship between this form of the radial solution and what I have written here. Okay. And then lastly, the choice of constant is for generic dimension, we'll say, and I'm not going to write this out exactly, you'll see. So in dimension n greater than or equal to 3, this is minus 1 over n times n minus 2 times omega sub n times the length of x to the n minus 2, where this omega sub n is the, if you like, you can call it hypervolume. We'll just call it volume normally. So it's the hypervolume of unit sphere in Rn, right? Which that volume depends on n, right? You can check this real quick by computing volume in the dimension 2 case and the dimension 3 case, right? Those are not going to be the same. Okay. Now, one slight warning. This sign here has been chosen for a specific reason. So the reason for the choice of sign above has to do with the, I would say it's typical, usually the typical convention that in many instances the operator I'm interested in is best treated as minus the Laplacian view. So I mentioned this before. I think I mentioned this in either yesterday or the day before lecture, how oftentimes this is the operator that we want to consider. It's not a big deal, but it's just good to be aware of this. So what this means is that basically what we would do is we would, for this operator, the minus sign would go from here onto the operator. So the fundamental solution for minus Laplacian in dimension n equals 3 would be 1 over 4 pi times the length of x, rather than minus 1 over 4 pi times the length of x. So first question, why these particular choices of constants, right? Because as we saw from our solution here, we were actually, it seems like we're free to kind of pick these constants as we want to, right? So then what is it that is best about picking these? There's a very specific reason why this was done. And here's the answer. So before I write down the answer, let's first ask ourselves, what is this a fundamental solution of? What is this doing? So maybe I'll move on for a second, and I'll come back to that question. So question, what does the fundamental solution do? Well, note that this fundamental solution, v of x, regardless of what dimension I'm in, right, for 2, 3, or higher, at the origin, right, where the length of x is 0, these all blow up. These are all undefined, right? So this blows up at the origin in all dimensions. So is this fundamental solution going to be a solution to Laplace's equation, right, on any domain, right? Including this origin? Well, no, right? No, because we've already mentioned that any solution to Laplace's equation on a reasonable domain, right, is going to be it's going to be infinitely regular, right? It's going to be infinitely smooth. So if it's infinitely smooth, it can't have points where it's not even defined. All right, in the interior of the domain, literally right in the middle of it, right? So this is no good. So it's not going to be harmonic, right? It's not going to be a solution to Laplace's equation. But you can check that the Laplacian of phi of x is going to be 0 at everywhere else. Okay, so this is going to be 0 for all x not equal to 0, right? So it's 0 everywhere except at the origin. Okay, but of course that wasn't the deal, right? When we're seeking a solution to Laplace's equation, we're seeking solution to Laplace's equation everywhere, not something that's allowed to exclude some points. So then the question is, when I write the Laplacian of this quantity, what is this? Right? Turns out that this is the delta distribution, right, in the sense of distributions. And so, going back to this original question, why did we choose the constants in the fundamental solution to be this way? So that the Laplacian of this fundamental solution is equal to the delta distribution exactly, and not some constant times the delta distribution, right? So not this thing, like some constant times the delta distribution. So these constants are chosen so that when I compute this Laplacian, it is exactly the delta distribution and not some constant times it, right? So it's exactly the impulse function that I expect it to be, right? The one concentrated at 0. Okay. All right. So, now the issue here, of course, is that kind of unlike what I did with some previous equations, this fundamental solution is not even a solution fully in the sense that I want, right? It's a solution everywhere except a point, but that's, close enough doesn't cut it, right? So then what is the point? What is the purpose of calling it fundamental solution? When something's called fundamental something, right? You would hope that if you've been labeling your things correctly, right, then it's important, right? So if you call something fundamental, that should be something important. And so why is it fundamental? So the point is that these fundamental solutions phi will be used to generate the solutions to Laplace's and Poisson's equation that I want. Now, we won't see some specifics there later, but here's a quick example. So this is this is from chapter 10. Okay. So this is material that, like I said, we will cover. We have a little bit of time at the end. So from chapter 10 material, a solution to Poisson's equation, okay, on R3 is the following. U of x is the integral over R3 of the fundamental solution in R3 convoluted with f. Okay. All right. So, in this way, right, our notation here, this phi sharing the same notation that we used for the heat kernel for the heat diffusion equation, is not, we're not misusing the notation here in this sense, right? Solution to this inhomogeneous Laplace equation, Poisson's equation, was given by convoluting my phi with f. Now you might complain that these are now no longer functions of a single variable. They're, functions in higher dimensional spaces. That's fine. We didn't technically go over that stuff, but there are analogs to this. You might also have complained previously when I wrote this that if this is the case, then technically this delta distribution is going to be like a higher dimensional delta distribution because it's going to, this phi itself is not, it takes in vectors, right, instead of real numbers, but it's the analogous thing. You don't have to worry too much about that. Okay. So physically, this phi is referred to as the electrostatic potential or Newtonian potential, at least in 3D, right? So in 3D, phi is electrostatic potential. Okay. Or Newtonian potential generated by unit source charge at the origin, right? So here's an interpretation of this. Okay, and so because getting more in depth as to how all of this leads us to being able to solve Laplace's equation takes a little bit too much time for what we want to do. That's pretty much it for Laplace's equation right now. And so our our goal here is to, so we're done with chapter 8 now. We're not going to do any of the rest of it. We are going to skip chapters 9 and 10 because that material is not needed for what we're going to do here. We may return to 10 a little bit later. And so we're on to chapter 11, which is Fourier series. Okay. Now, what is kind of the core idea behind the Fourier series? So Fourier, like in his very original work, he wrote down a bunch of statements, claims, and proofs using these claims that essentially any function could be written in some appropriate sense as like a linear combination of sines and cosines, right? Where, of course, this may be an infinite combination, so there may be infinite series involved, okay? But basically, any function you can dream up, you can write as just a linear combination of sines and cosines, okay, in some way. Of course, a lot of this wasn't believed when it was originally introduced. And some of the details are wrong. That's not that important because technically you look at it that way, like most, most any kind of analysis done before Weierstrass is technically, you know, not on completely solid footing, but that's okay, it doesn't matter. These claims are ultimately completely justified. You just have to be a little bit more careful with the details, but everything works out fairly nicely, kind of miraculously so. And so, what is a Fourier series? So first, we start with a function. We'll call it phi of x, defined on an interval 0 to L. Now, this is intentionally an open interval here because, as we're going to see, we don't really care about the value of this thing at the endpoints. Okay. And so, and we'll say why later. This ultimately is not going to matter for us. But we take a function that's defined on the open interval 0 to L, and we try to find coefficients. We'll call b sub n, where n is 1, 2, and so on. Okay, such that this phi of x can be written as a sum from n equals 1 to infinity of b sub n times the sine of n pi x over L. Okay. So exactly what I was saying in the little intro here, where if you think of like the original claim of Fourier was that basically almost any function you could dream up can be expressed as some kind of linear combination of sines and possibly cosines. This is me trying to take a function defined on an interval and write it as some infinite sum of some coefficients, right, some real numbers, times sine, right? So some infinite linear combination, if we're thinking of like linear algebra terminology here, some infinite linear combination of sines. Okay. Now I've chosen this in a particular way here. So first of all, note a few things. So one, what occurs at the endpoints here in this sum? Well, I have zeros, right? So if x is equal to 0, of course, we're talking about phi defined on the open interval, so whatever. You might say, well, maybe phi doesn't even have values here. But at 0, right, this is sine of 0, so that's 0. And at L, this is sine of n pi, so that's also 0, right? So the expression has zeros at x equals 0 and x equals L. Okay, that's the first thing. Okay, of course, these functions here written in this way have increasing frequencies, right, or their period decreases because of how this is written. Okay, we'll do some plots of these for some of this. But what do I mean by this equal sign? What do I mean? I start out with a function phi. Phi of x might be a constant function. It might be 1, right? It could be the function phi of x is equal to x, right? So when you think of function, phi of x could be, 1. Phi of x could be e to the x. Phi of x could be just the identity function, just x, right? So all of these, this is what I start with. And then I'm making a claim that these things are equal to this infinite sum. Well, when I say that these things are equal to some infinite sum, then I'm saying something about convergence, right? So, this is a statement about the convergence of the sequence of partial sums which is s sub big N of x, which we can define to be just this expression summed up to big N, right, instead of to infinity. So this is n equals 1 to big N of b sub n sine of n pi x over L. Okay, and so really what we're saying here is that we have found coefficients b sub n such that this sequence of partial sums converges to phi. That's what we're saying as big N goes to infinity. So really we're saying that we find b sub n such that s sub big N of x converges to phi of x, right? For any x chosen in 0 to L as big N goes to infinity. This is what we are claiming here when we say that this is equal to this. Okay. So we have some big questions here. Questions. Can we do this? That's a big question, of course. Secondly, if so, how do I find the b sub n's? And thirdly, what is it about sines and cosines that allow us to do this, right? What is it about sines and cosines that are so nice here? Or that is so nice that would allow us to do this. Okay. So the answer to can we do this is yes, if phi is reasonable, right? So under some very mild assumptions, can we do this? Yes. That's pretty amazing. If so, how do I find the b sub n's? We'll see here in a second. What is it about sines and cosines that is so nice? We'll see later. We'll see later, but also we're about to see most of the answer right now. To speak a little fast and loose right now, from linear algebra, right? So recall linear algebra, and specifically recall what it meant to have a basis for a vector space, right? So what does it mean to have a basis for a vector space, right? Well, it means that any vector in your vector space can be written as a linear combination of those vectors. Well, you might remember these were usually some like edge case examples in linear algebra that vector spaces were allowed to be infinite dimensional, right? So they were allowed to be infinite dimensional, and in that case, of course, these linear combinations would involve infinitely many basis vectors, right? So in fact, if a vector space is infinite dimensional, it means that there is no finite spanning set, right? There's no finite basis. There's no basis. There's no set of basis vectors there is no basis that has finitely many vectors in it, basically, for the vector space. Well, the canonical examples of vector spaces that are infinite dimensional are function vector spaces, right? So the space of continuous functions on a closed interval, right? That's a vector space with respect to pointwise addition and scalar multiplication of functions. It turns out that the sines and cosines are a basis for reasonable functional vector spaces, right? Meaning that anything in those function spaces can be written as a linear combinations of sines and cosines. Okay. Well, you might also remember from linear algebra that one of the nicest things a basis could have, right? One of the nicest properties a basis could have is that it's orthogonal, right? Orthogonal, meaning that the dot product of any two distinct vectors was actually 0. An orthogonal basis was extremely nice because it allowed you to compute the actual linear combination coefficients in a way that was extremely easy, right? They had a representation that was very, very easy. You could immediately compute them. Normally, to compute those things, you had to set up, a system and solve. You had to set up a matrix equation and solve it. But you don't have to do that with an orthogonal basis. You can actually compute it directly from the basis vectors just by computing the dot product. Well, you might also recall that the dot product was called the inner product. That was another name for the dot product. And it turns out that for an infinite dimensional vector space, there are notions of a dot product that we can define. And it turns out that sines and cosines are not only a basis for reasonable function spaces, they're an orthogonal basis. Okay, so they're a particularly nice basis. And so that's really what's going on here. But let's actually find the answer to 2 right now. How do I find the b sub n's? Well, first, note the following identities that you are going to have to show in your upcoming homework, which will be posted very soon, as I keep saying. Note that there's a couple of things, right? One, if I integrate from 0 to L, sine of n pi x over L times sine of m pi x over L dx, this is actually 0 if n and m are different. This is called an orthogonality relation. You can verify this yourself, and you will just by directly integrating this. Okay. And secondly, what if n is equal to m? So what if n and m are equal, so that this is sine of n pi x over L times sine of n pi x over L. So this is like sine squared of n pi x over L. So what is the integral from 0 to L, right, of, I'm using script L in the in the limit and big L here. That's confusing. There, let me switch back to what I was doing. So this is the integral from 0 to L of sine of n pi x over L all squared dx. Right? And this is L over 2, it turns out. You can also check this via direct integration. So if n is equal to, or if n and m are different, this is 0. But if n and m are equal, then this expression is L over 2, something really simple. So I can use this fact, I can use these two facts to find the b sub n's. Okay, so I have these two facts, which I can verify just by, like, Calc 1 style integrating, right? And now I can use these to compute my b sub n's. Okay, so note the following. Note that if I were to integrate from 0 to L the given function phi of x times sine of n pi x over L dx, right, then what am I trying to do here? So what I'm trying to do is I'm going to say, okay, suppose that for this phi, I can find such a series. So let's go back to my questions. We asked the question, can we do this? Let's say that we have discovered the answer is yes. That still doesn't necessarily answer how do I find the b sub n. So we're assuming the answer is yes. So yes, I can write phi of x in this form. So if I can write phi of x in this form, I just don't know what the b sub n's are. So that's what I'm trying to figure out. So say that we can do this. Let's find out what the b sub n's are. Okay. Well, here if I integrate phi against sine of n pi x over L dx over this integral 0 to L, or sorry, this interval 0 to L, then this is the integral from 0 to L of phi can be written, I'm going to use m as the index so that I don't confuse it with n here. So this is a sum from m equals 1 to infinity of b sub m sine of m pi x over L sine n pi x over L dx, right? Now what I am going to do is I am going to interchange this integral and this sum sign. This is something that whether or not this can be justified is a tricky thing. We're going to go ahead and do it and just hand wave for a second, but this can be justified. But this is exactly the sort of operation that mathematicians used to do in the 1700s and 1800s, like kind of willy-nilly, that was not always justified. But it turns out in this case it is. So this is equal to the sum from m equals 1 to infinity of integral from 0 to L of b sub m sine of m pi x over L sine of n pi x over L dx. But then by the orthogonality relations that we've written down here, the first one especially, right? So by the first one, this integral is 0 if n is not equal to m. So most of these terms are going to be 0, except when n is equal to m. And so in that case, all these are going to be 0 except when n is equal to m. So we have b sub n here, which I can move out. This is b sub n times the integral from 0 to L. All these integrals render this 0 except when m is equal to n. And so we have the integral from 0 to L of sine of n pi x over L squared dx. But from the second orthogonality relation, that integral is just L over 2. So L over 2 times b sub n is what I get when I do this integral. Oh! But that means that b sub n is just 2 over L times the integral from 0 to big L of phi of x sine of n pi x over L dx. Ah! And so, let's go over what it is that we have done. We have wanted to write a function, phi of x, as this infinite sum. The sum from n equals 1 to infinity of b sub n sine of n pi x over L. Okay, say that we can do this. How do we find out what the coefficients are? We integrate the function that we're given, phi, against sine of n pi x over L dx, and we do that integral from 0 to L, and we multiply by 2 over L, and that gives me each of the b sub n's, right? So the dependence on n here is coming from this inside the argument of sine here. Okay. Does that make sense? Well, it makes sense that the b sub n's would be tailor-made for the function itself. So of course it makes sense that in order to find the b sub n's, this definitely depends on phi, right? So different phis are going to yield different coefficients. That 100% makes sense. I did not expect to find one set of coefficients that works for every single function. That doesn't even make any sense, right? So this is exactly the sort of thing I would expect out of this. And so if we define b sub n in this way for given phi of x, then the expression of writing phi of x as the sum from n equals 1 to infinity of b sub n sine of n pi x over L. This is exactly called the Fourier sine series. So this is called the Fourier sine series of phi of x. Okay. And I should say that obviously this depends on the interval as well, so maybe we should include here the Fourier sine series of phi of x on the interval 0 to L. Okay. Well, let's do the same thing with cosines, right? So now let's try to do the same thing with cosines. Okay, so let's ask, can we write phi of x, right? So can we write phi of x as the following? I'm going to separate off the first coefficient in the cosine series. Of course, remember, cosine's an even function. The reason I'm doing this is because I want the formula I come up with for the coefficients to be the same for any n. I don't want to have to single out the n equals 0 case. So I'm going to write this slightly differently. I'm going to write this as 1/2 times a naught plus the sum from n equals 1 to infinity of a sub n cosine of n pi x over L. Okay, again, if you're immediately very, violently resisting this 1/2 a naught here, that's purely so that my formula for the coefficients, my formula for the coefficients can be stated in one line. I don't have to write out a second case. Okay, you'll see when I state this here in a second. So it turns out that cosine also has orthogonality relations. Which I'll state in two lines, or I'll state in one as like a piecewise thing here. That if I integrate from 0 to L cosine of n pi x over L times cosine of m pi x over L dx, this is equal to 0 if n is different from m, and it's equal to L over 2 if n and m are equal. Okay. And so, similarly, if we integrate from 0 to L phi of x against cosine of n pi x over L dx, what I get is that this is equal to L over 2 times a sub n for n 1, 2, and so on, if n is equal to 0, right, the n equals 0 case, then if I integrate from 0 to L phi of x dx, I get that that is equal to 1/2 a naught times the integral from 0 to L of 1 squared dx, if you like, right, which is L over 2 a naught. So here's exactly why this 1/2 was included, so that I would also get L over 2 times a naught in the n equals 0 case, so that when I write this here in a second, I'm going to be able to do it on one line and not have to do stupid stuff. So thus we have that the coefficients a sub n that allow us to do this is 2 over L times the integral from 0 to L of phi of x cosine of n pi x over L dx, and that is for n equals 0, 1, 2, and so on, right? So I don't have to single out the n equals 0 case differently. There it is. If I define my a sub n in this way, then this series on the right-hand side is called the Fourier cosine series of phi. Of phi of x on the interval 0 to L. Okay. All right. Okay. And so what does all this allow me to do? So first of all, I need one more tool before I can move on to sensibly talking about these things. So there's what's called the full Fourier series. What is that? So here we are given phi of x on an interval minus L to L. And if you're immediately noticing, wait, for the sine and cosine setting, we were given the function from 0 to L, right, in both of those cases. So why now are we switching? We'll see all of this stuff, okay, especially when you start looking at pictures of this stuff, it starts to make a whole lot more sense. But we'll see, we'll make sense of all of this stuff. So here we're given phi of x on the interval minus L to L, and we wish to write phi of x as the following series. So we want to write phi of x as 1/2 a naught plus a sum from n equals 1 to infinity of the following: a sub n cosine of n pi x over L plus b sub n sine of n pi x over L. Okay. Okay. So first, note that if we pick any two of the list of functions, we'll list them like this. So 1 cosine of n pi x over L, sine of n pi x over L, and we consider these for n in the natural numbers, so n can be whatever here. If we pick any two out of this hat, right, this big hat containing all these functions, pick any two you want and multiply them together and integrate them over L to L. So pick any of these two functions, multiply and integrate them over the interval minus L to L. We'll see what we're doing here is actually we're computing their inner product, right? So the analog of the dot product for us for finite dimensional vector spaces, we're doing this for infinite dimensional vector spaces here. We're computing their inner product is what we're doing when we say to do this. So multiply and integrate them over minus L to L. We'll see that we're actually computing the inner product fg, or f dot g if you want to think of it like that. Okay, when we do that, what do we get? We get that if we have chosen, say, two cosines of the same n, right? So I get cosine squared of n pi x over L. Well, from minus L to L, this is actually just L, but that's the same as if I did this for sine. Okay, and of course, if I did this for 1, if I picked the same, so this is 1 squared dx, so then what I get here is L plus L, so I get 2L. Okay. But the rest, any other combination yields 0, right? Any other combo yields 0. Again, by those orthogonality relations. So I have an orthogonality relation for this list of functions. And so using the exact same argument as before, what do I get? So by the exact same argument as before, a sub n can be defined as 1 over L times the integral from minus L to L of, think of why this is 1 over L now instead of 2 over L. Phi of x cosine of n pi x over L dx, and that is for n equals 0, 1, 2, and so on. And b over n is 1 over L times the integral from minus L to L of phi of x sine of n pi x over L dx, and n is 1, 2, and so on. Okay. Okay, so now the full Fourier series define a sub n, b sub n as above, right, for given phi of x on minus L to L. Right. Then the full Fourier series for phi of x on minus L to L is this thing. It's 1/2 a naught plus the thing I wrote at the very beginning. So it's the sum from n equals 1 to infinity of a sub n cosine of n pi x over L plus b sub n sine of n pi x over L. Okay. Now, your first question is going to be, what does any of this have to do with solving PDEs, right? So as we'll see, this is going to give us exactly the tools we need to solve PDEs via separation of variables. So that's where we're headed. We haven't separated a single variable yet. We haven't talked about a PDE yet in this part. We're just writing Fourier series. And it turns out that understanding this bit of it is probably the most important bit of understanding how to compute these solutions via separation of variables, because separation of variables, as you'll see, we're going to do tons of examples of this stuff. Separation of variables is a very, very mechanical process. Okay, so once we get the algorithm down, it kind of always goes the same way. There are kind of some like very distinct like classes of examples, and pretty much everything that falls into each class of examples behaves in a very similar way, which is good in the sense that it means you're going to be able to apply this to like anything that falls in those class of examples and solve in a like purely computational mechanical way, and it's great. The only bad thing about it is that it's applicable, in a very narrow direction, and it's not, there's, there's more broadly speaking in PDE, there's just a lot more to it, as we've seen, right? We haven't even touched on that. In a typical PDE course, you might see a huge chunk of the course, like the vast majority of the course, devoted to this. So for us, we're devoting roughly like 1/3 of the course to it, which I think is perfect. So anyway, I think that's all I'll say for today. Next time I'll do a few examples of these Fourier series and show you some pictures so that you can see what the Fourier series is actually doing for these functions. So we'll look at some pictures to see what it is that's actually happening, and then we'll do a lot of kind of the background for why this works in a quick way that's going to rely heavily on linear algebra. So over the weekend you may want to kind of brush up on some old linear algebra knowledge, especially vector spaces, basis of a vector space, an inner product on a vector space, right? What it means for vectors to be orthogonal, what it means to have an orthogonal basis. All of these are very important. And if you understand generally what's going on there, then passing to infinite dimensions is not so hard. You're not losing out on too much by treating the functions in your head as vectors, as just any old vectors, right? Even if they're technically these like vectors in an infinite dimensional vector space. Anyway, so I think this is a good stopping point. So we'll start on Monday again with examples of Fourier series and how all of this kind of ties together what it's doing. And we'll continue on from there. So anyway, I will see you on Monday. Have a good weekend. And as I said, I'll post homework that'll be due sometime next week. You'll have plenty of time to do it, so don't worry too much about that. Anyway, so I will see you all later.